right, so let's get started. So yesterday we saw a very simple language of expressions where we had natural numbers, booleans, additions, and conditional branching. And then we saw that we could write some garbage programs. And as a consequence, when we were writing the evaluator, we had values for the programs that made sense, but we also needed to have a placeholder return value, the nothing in the maybe monad to describe a failure. And then we saw how we could write this evaluator using do notations and the semantic version of addition and everything else. And then what we looked at is introducing a type system to our small language of expressions so that we can guarantee that all of the programs we write actually make sense. So there was a bit of freedom in how we added types to this language. We decided that if you have a natural literal, then it's an expression eventually computing a natural number. If you have a boolean, it's the same for bool. If you're adding, we explicitly request that both expressions are natural numbers. So we're not doing any implicit casts from bool to 0 or 1, for instance. We demand that both arguments are nats. Yeah. And then for conditional branching, we said, well, the conditional better be a boolean, because this is the one telling us whether we're going left or we're going right. But then the branches can have an arbitrary type, just as long as it's the same type in both branches, because then we can predict what the type of the overall expression is. It's going to be the type of both branches, because we will definitely be going down one branch or the other.
Yeah, I think there is a thing to say, just that here in the type, so texpra is indexed over this type tie, which also has constructors nat and bool. Ooh. And I mean, you pick your cognitive load. We're calling them the same names as the nat and bool constructors that embed literals into expressions, so that we don't have to remember more than one word, right? We know that one of them is a constructor of texpr and the other is a constructor of tie, even though they're called the same thing. So here, we're not doing overloading to confuse you, we're doing overloading to have fewer things to remember.
And then we saw a couple of examples. So the good sum example that we saw at the very beginning was still type checking, because it was adding two natural numbers and that's just well typed. And then the bad sum example was simply rejected now, because we're trying to add a natural number with something that's a boolean, and they're just not allowed by our type system. So we've managed to remove a lot of the garbage from the input language, and then the cliffhanger was the impact of this modification on the evaluation function. And so I don't know if some of you have tried to define the typed, the notion of type values. So just like expr is, texpr is indexed by type, so is the type of values. And then there's different ways you can play that game. I'm going to case splits on the type. Ooh. There we go. And if I have a boolean, I'm going to say that the type of values is actual booleans, like actual, true or false. And if I have a natural number, the type of values will be actual natural numbers. So 0, sucks, and etc. of natural numbers.
Yeah, so here color, if you can perceive it, is doing you some favors, right? This red bool and this red nat, they're just constructors in an ordinary inductive data type. They are just syntax. And here we're saying, actually, each of these syntactic things corresponds to an actual AGDA type of stuff. the value, the sorts of values, how AGDA represents the sorts of values we were expecting to get out of this thing.
So I'm doing this because there's no overlapping between the two notions of values. And so I can just dispatch on the type and say, okay, I'm sure the bools will have this shapes and the nats will have this shape. If it were not quite the case, maybe we'll have time to see a more complex example later on. You could instead, for instance, define a type family, which is similar to the one we had at the beginning. So let me comment this out quickly. So we started with this family of values, which had the same components essentially, except that you see here it's not constrained by the type, but we can make it so. And then the sensible thing to do is to say that
you need some extra T's.
Yeah. That the injection from natural numbers into values is going to build like a natty type value, and the injections from booleans into the types of values is going to define a boolean kind of value. And so this ensures that, I guess we then see it in the type of tval. Tval is saying something like full T. So we don't want to write an evaluator only for Boolean expressions or natural or expressions computing natural numbers. We can take an arbitrary expression.
That dot's not AGDA.
Of type T.
Yes.
Yeah. And then we'll compute a tval of the same type. And hopefully we won't need maybe. So let me just revert this back.
So the only difference between these two ways of doing it are that the data way gives you an extra layer of wrapping, which we would then have to put on and peel off all over the place. So we're going to go with the green one. Do you want me to do it? It's crazy talk. Okay. So I'm going to introduce my expression, and then at some point I'll get tripped up by a keyboard. But we'll cross that bridge when we come to it. Right, so same deal as before. We've got to look at the expression to see what sort of a thing we're evaluating. So case split on that, and then the usual round of renaming all the things. Reload. Okay, now enjoy the refreshing difference. Let's look at the puzzle we're in. Oh, can we make this go? How do I?
Yeah.
What's embiggen?
Control scroll into.
Right. Okay. So you can see the deduction that happened here. By discovering that the expression was made with nat, we discovered that it was an expression of type nat, specializing purple T to nat, causing green tval to compute the type nat, which, it's really fortunate that that's exactly what we want, because it's exactly what we've got. Meanwhile, the exact same thing has happened in the other direction. In this case, you can see we want a tval bool, and when we look a little more closely, we see that that computes the bool, which is exactly what we've got. Right. Next up, in the add case, we're asked for a tval nat, which is an honest to goodness AGDA natural number. So we can actually hope to compute it by doing honest to goodness addition. Right, at which point we need some AGDA numbers But fortunately, that's what AGD gives you when you evaluate natural number expressions. Oh, fortunately plus is commutative, but even so. So that does, of course, demonstrate that there are still ways you can get this wrong. Okay, so that's nice. So, you know, no messing about, no wrapping, no unwrapping, no error cases. All the pieces just fitting together sweetly. Likewise, I believe we have an if-then-else, do we not?
I hope so.
I mean, if we didn't, it wouldn't be the end of the world. Right, so here I have to give an actual bool. Oh, what did I do? I hit the wrong button. Now I'm hitting the wrong button even more times. Right. So fortunately here we can give the Boolean goes in a hole. It's nice to notice that the other ones don't. We can evaluate the Boolean expression, and that is spurious yellow. And then here we want to t-eval et. Now we could again get this one. We could get wrong. We could get them in the wrong way round. But at least we've got as far as making the pieces fit together well enough that we can say there's no garbage in, so we don't have to worry about or model what it is to have garbage out. So that's the key piece of progress. Yeah, this program it's a late 90s program. Who's next? Do you want to?
You want to do some examples?
Yeah, that's a good idea.
I mean, yeah,
We
you
should
know,
always do examples.
it's one of these classic things, of course, dependently type programs. Go, isn't it wonderful that this program type checks? So, nobody ever runs it.
Yeah.
Or at least that's true.
Right, so let's see. Well, I guess I can do just evaluation. So I'm going to try to evaluate the typed good sum. And just to remind you what it was the addition of 42 and 10. And it does evaluate to 52. And this time around, because we've had this type of values which is computed by inspecting the type of the expression, we don't have any wrapping, unwrapping, and so on. So instead of having just nat 52 like with the previous evaluator, now we just have straight up the value. Is there any other example you had in mind?
Nope.
Okay. Okay, well, I guess I can keep going with this thing maybe, and you can do inference. Right, so, but then the question is, okay, we have this really nice internal language, which is strongly typed, and we can write an evaluator which doesn't make any mistake. Well, we don't know if it makes any mistakes, but it doesn't need to handle any error cases. But how do we get to here? So if you get a user program as an input, it quite probably won't be in this format. It will come in as a string or like the content of a file. You'll parse it, and there will be no intrinsic type enforced constraints. So you will probably get something that looks a lot like one of these expressions, which may be correct, may be incorrect. And then the idea is that, I don't know if you've seen this slogan in 316. In functional programming, we like to say that we parse, we don't validate. So instead of checking that this expression is valid and then processing it, But because you haven't built all the invariants into the representation, you still need to handle like the potential error cases, even though there shouldn't be any because you've checked that the expression made sense. Well, we like to instead transform the original expression into something more structured, for instance, these typed expressions, so that then you can apply functions that are completely total on them and are guaranteed to never encounter a bad case. So you do the parsing, which is from unstructured data into structured data. This step can fail because your unstructured data might actually be invalid somehow, but then you can send back a meaningful error message. And once you have the structured data, because so much information is enforced into the inductive definition, you can actually have your really fancy, clean definitions processing it. So here what we're going to do is explain how the expressions with a lot of invariants built in relate back to the original expressions in the language with not that much information. And then we're going to prove that, to write a function that attempts to make sense of the unstructured data as something more structured, whilst proving that it is actually related to the original one. Okay, so let's have a look. And how do we say that a typed expression corresponds to like an old untyped expression? Well, we simply explain what the less fancy version of the typed expression would be. So if we start with a NAT, a literal of type NAT, the less fancy version is looking exactly the same, except that it's not actually containing any type information anymore, right? So for the Boolean, it's going to be the same. It's purely syntactic translation. For addition, well, it's also going to be an addition node. And then if you look at the type of the goal, you need to feed in sub-expressions, and all you have is sub-typed expressions. So you call the erasure recursively. And for if, there's going to be the same. Do I dare to use auto? And of course, it's doing something
You might
silly.
feel like if you ask it to, it might be one of the top 10 hits.
All right, maybe. Let's try.
In fact, there's a lot of crap that it could possibly be.
Well, you could even use some constructors, yeah. So let's see. So it tries
No, we're
to
not
erase the
getting anywhere near
Boolean, the
it.
left
Yeah.
branch, the right branch, some constant values, or even add stuff. Okay, that's. So what we want is to preserve the structure. So we're just, I mean, I should just copy paste this stuff, but EB, ET, EE. And
You might need.
I think you just need more brackets, right?
You might need more brackets. It might.
oh, I see. It could be.
Yeah.
It's just annoying.
Doesn't know how outrageously nested they are.
Well, because it's the same symbol on both sides, right?
Yeah.
If we had broken the symmetry, it would have been a lot better.
Yeah.
Okay, that's nasty looking, but it's the way it is. Yep.
Oh, what does the vertical lines do again?
Oh yeah, so it's just the name of the function.
So what and surrounding ET,
Yeah, so this is the name of the function, erasing the typed expression, and here I'm calling it on EB. So remember that when you have an underscore in an identifier, this means this is where the argument goes. So here we happen to put it in the middle.
oh,
Yeah. This is just. typical excessive AGDA programmers making function names look weird in order to mimic mathematical notation.
Right, so forgetting information is really easy, right? We just throw it away and that's it. Going in the other direction will be a bit trickier because now we're starting from something unstructured and we have to make some observations that will ensure that we can actually build such a typed expression thing. So for that, I'm going to give you the definition. So constructor make Welltyped. We'll explain what it means for an expression with no invariance whatsoever enforced inside to be well-typed. Well, first it needs to have a type, so I'm going to give myself a type. And then I better have a term of that type, so a term which has type tx per of a type. And now I need to relate this expression I started with the thing I'm ended up with after the elaboration. And so I have this proof that, let's see, if I erase the fancy version of the expression, I should get back the original one. I guess I can open Welltyped in case we want to. Oops. And now Fred will show you how to build such a thing.
One microphone is enough.
I didn't see it.
So notice that, so here we're saying that an expression is well-typed if there is a typed expression which is basically the same thing as E, right? So we need this last field because otherwise we just pick our favorite well-typed expression. So the idea is that we could try, given an expression, to prove that it's well-typed, right? But if we start doing this, well, let's maybe just do it, and then we'll see what goes wrong. Because this is a very suspicious type, right? In the sense that we know that not all expressions are well-typed. So, but we are claiming that for every E, we can give a proof of its well-typedness. Let's see how far we get. So I'm going to pattern match on the E, do the usual renaming. Okay, so I start here with an untyped expression, and then here I have to come up with a proof of well-typed not n, right? Okay, so I have a constructor for doing this, so I can refine, and then I have to fill in the fields of this record. So I have to give a type, I have to give a term of that type, and I have to give a proof that if I apply this erasure function to this term, then I get the thing I started with, right? So in this case, I can kind of work backwards because I need something whose erasure is not n. But if I look at the erasure function, the only way I can produce a not n is if I feed in a not n, right? The only thing that erases to not n is not n, the type not n. So that means, well, that here I want to do not n, because then my goal, if I fully normalize it, just becomes not n equals not n. Okay. And then here I have to give a type, but that should be the type of not n, so I can actually solve this goal. No auto needed. Just solve it, Control C, Control S, and it has to be the type not, right? Because that's the type of this thing. And similarly for Booleans, well, here I want to give a type, a term of that type, such that if I erase that term, I get a bool. Well, I know that my Boolean is a Boolean. So my term type is bool. I know that the thing I want to kind of erase to be bool b is going to be bool b. So that my proof is really easy, right? Okay. But now here my problems really begin, because I have en and em as sub-expressions. I know that in the end I want to give a type here and a term which erases to this addition, right? So I know that this better be add of something something. Oh, that's the wrong goal. And here I would like to put in kind of the result of inferring the well-typedness of the sub-expressions, right? But infer of en, for example, well, that shows that en is well-typed, but doesn't mean that if I want to use add here, then I need this thing to be a natural number, right? But there's nothing stopping me from writing bool true plus bool false here in my input term. So I can't guarantee that this thing really is. I mean, I can guarantee that this is well-typed maybe, but I can't guarantee that it's a natural number, which is what I need here, right? So I think, again, I have to retreat. I can't promise that everything is going to be well-typed, but I can promise to maybe produce a proof of well-typedness, right? And then we have the same thing again, but in these cases, we are just happy. And here, I don't know yet. So the nice thing now is that I'm back in maybe land, so I can use do notation for maybe and try to do things. So I will try to infer en, and I will try to infer em. Okay. And then here I can pattern match on the left because I know this is a record. So this is definitely going to be given by the only constructor. Make well-typed tie term proof. Similarly here. Okay, so let's see what we have. So I have some type tie. I have some term tum, and I have a proof that if I erase this term, then I get en, right? But now I'm only really happy if the type here is not, right? If it's a Boolean, then it wasn't well-typed to start with because I'm trying to add this thing to something else. So I'm going to just pattern match on this being not. Okay, but then Agda complains that you haven't dealt with all the cases. There's also the case where this is actually a Boolean. Okay, that's fair enough. So I'm going to say, well, if it's anything else, then I'm just going to give up with a nothing. Right. And similarly here, if we now look at where we are, then we see that actually these two things are now natural numbers. So it does make sense to say add tum prime, right? That is an expression which is a natural number. But, okay, I have to give three things. I have to give a type. Well, I know that the type I'm inferring for this expression must be not. And I'm claiming that the expression I have here is going to be add of term and term prime. And then what do I need to prove? Well, I need to prove that if I erase term plus term prime, well, we define the erasure of an addition to be an addition of the erasures, right? So that's why this thing here has computed a little bit. And I need that to be equal to this, but I know that this bit erases to EM, and this bit erases to EN. So if I pattern match on these proof as REFL as well, then actually REFL just works here, right? So a lot of work is being done behind the scenes by this kind of catch-all saying, well, if this pattern match doesn't work, then we're just going to return nothing. Right. Okay. And then here, we could try to do the same thing. So the pattern we had was we just infer all of the sub-expressions. Okay, and then we know that they are going to be make Welltyped. And actually this one we are only going to be happy if it's a Boolean, right? So I'm just going to pattern match on bool immediately. And then here I have some term and some proof. And otherwise I'm going to be unhappy. Okay, so I have, oops. Okay, so let's see what we have. So we are sure that this term we have, TM, is actually a Boolean. So, okay, we could try to produce this thing. So we're saying make Welltyped something, something, something. Okay, and the term we want was an if then else of term 1, well, something, something. So because I pattern matched on bool here, I know that this is a Boolean. Otherwise, I'll have this case. But then here, I now have to give a typed expression of type goal2. And here, I also have to give a typed expression of goal2, right? But what should I use? I really have two candidates. I have type 1, which is a type, and I have type 2, which is a type. But I'm only really happy if these are the same, right? I need both branches of my if then else to have the same type. So now my trick of just pattern matching on the types doesn't work anymore, because I'm not allowed to say, well, I want these to be the same, right? Well, it looks like I'm allowed to do this, but all that's happening is that I'm now shadowing this variable. So if we look here, we see that we have type 1, and then we have another type 2, which is not in scope anymore, because we've used the same name, right? It's like saying lambda x goes to x. So just pattern matching doesn't cut it anymore, unfortunately. We need some way of checking if these two types are the same, right? So up here, I'm going to define a function which takes a s, which is a type, and it takes a t, which is a type. And now, if I was being principled about it, then I would probably either return a proof that they are the same or a proof that they are different, right? But in a way, because I'm living in maybe land here, I could also just maybe return a proof that s equals t. So in the happy path, I'll get a proof that they are the same. In the unhappy prof, I'm just going to return nothing, which is kind of what my infer function is doing overall, right? If I had a more precise infer function which gave back an error message saying what went wrong, then I would like to propagate that error message to this function as well, right? So I could say, okay, couldn't infer a type for E because nut is not equal to bool, right? But here I'm just going to say nothing in that case. Okay, so how do I define this function? Well, I just have to look at S and T, right? So I'm going to pattern match on them. And then I'm going to take my two happy cases, put them at the top. And in all other cases, because I'm not actually producing any evidence, I'll just say nothing here, right? Whereas here, I'm deciding is bool equal to bool? Well, yes it is. So I'm going to say just, and then I have to give a proof for bool equals bool, that's REFL, right? And similarly in the nut case, right? Okay, so I have this function that decides if S and T are the same. Maybe they are, maybe they're not. So now I could deploy this function here, right? So I can say, okay, let's check if tie1 is the same as tie2. And because I'm in this maybe do block, I can just do it as part of the do. And then here now, because the do block only deals with the happy path, right? And in the happy path, this function returns just. So R here is a proof that they are the same. And now again, I can pattern match on R as REFL. And now if I look, they are actually the same, right? Because I'm now going down the happy path where they are the same. So here I can now just give back tie1 as my type. And then here, I now need a type expression here. That's term 1 and term 2. And because I pattern matched on REFL, they have the same time. So that makes sense. And then here again, I get something that looks a bit strange, but it's an if then else. I wonder if I can get away with just pattern matching.
Nearly there.
Oh, I didn't pattern match on this one. Right. So that's how it works, right? So I'm pattern matching on all the subproofs, which says that the erasure of this term is EB and so on. So that when I get to this point, because I've given the same kind of term but with more informative pieces, then that's the evidence that I had something well-typed to start with. But of course, this could have gone wrong if this wasn't actually a Boolean. And this equality check could have gone wrong, right? This is returning nothing in a few places. So I guess we could try and actually run this. So we had some examples that worked up here. So if we take a good sum, okay, so we see that if we are, so a good sum was an untyped expression. If we try to run the infer function on it, then we get a just, we succeeded. And we have inferred that it's a nut, and it corresponds to this typed expression, which looks the same, right? If we do a bad sum, then we just get nothing. And if we do this one, then again we get something sensible because all of the branches were actually the same here, right? If I change this. So remember, so here my two branches are different, but if I try to evaluate this thing, then that still succeeded because this Boolean was true, so we never go into the bad branch, right? But if I now try to infer it,
Well, it's not even a bad branch per se. Right? It's just that the two branches
Yeah.
mismatch.
we see that this actually doesn't have a typed correspondence because the two branches have different types, right? But so the nice thing now is that all the possibilities of going wrong are basically here in the infer function, right? This is the thing that can return a nothing. And then if you evaluate using this function, there are no nothings anymore. So we don't have to do all of these checks at every step. Did the sub-expression fail or not? We can just immediately do the addition, for example, rather than first evaluating this, checking is it just or nothing, then evaluating this, is it just or nothing, and then only in the good case do this. Right. So it's, in a way, it's a more efficient way to do it, to contain all of the failure in one step in the beginning and then work with a nice expression. Okay, should we?
I can do some more. So, yes, so as Fred was saying here, the difference with evaluation is that we are actually checking everything, right, in the if then else. And that's because we are building this data structure with a lot of invariants inside, and there's no way to say, well, I'm only going to check half of it, whichever we execute. So you need to clean up everything. I did want to...
It is very noticeable. There's it's a very common pattern of programming in this style where if you're interested in generating, so doing some form of testing that generates evidence, you first of all write the function which throws the evidence away, and then you show you can invert that or partially invert that. So that's what we did here. We wrote the function which throws away type information and then says, you know what, we can run that backwards.
Yeah, and actually if you're trying to build like the wrong like intermediate, the wrong typed representation for the original program, because you have this constraint on the fact that erasing the fancy version back to the user input actually gives you the user input, there's a guarantee that you cannot swap the two branches of the f around, for instance. Or, okay, this is fairly simple, but you can imagine that if you have a much more complex syntax, it can be really helpful because it allows you to track any sort of typos you might have made.
Yes, it's very easy to give back the well-typed version of any old shit. But this thing doesn't give, this promises to give you back the well-typed version of your expression if it's going to succeed at all. So,
And one thing I like to do, but I mean this is maybe personal preferences, is that now that we can actually check equality between types, instead of having explicit error handling in these cases where the things you're adding up are not nuts, you can say, I'm willing to accept any type whatsoever as long as it is equal to nuts. And because you're only considering the happy path here, REFL will substitute nat for Taiwan in the rest of the program. And you can do the same here, Tai2, and then REFL Tai2 equals nuts. And then you can do the same here, Tai0, I guess. And then EggTie, well, REFL, EggTie, Tai0 on bool this time. And this way you're not saying nothing anywhere anymore. You're only talking about the interesting cases, the positive cases, right? Okay, so one thing I was thinking whilst Fred was filling in this program is, how do we even prove that this notion of well-type makes sense? What is a good property for it to have? Well, one thing we may want to prove is that typing unique. If for a given expression you have two competing proofs that it's well typed, then they are actually giving you the same answer. Oh. Okay. That could be a sensible notion of what it means for the typing to be a sensible notion, right? It's like, well, the programs, we don't just assign them random types, right? We assign them, in a sense, the only one they could possibly have. So that's one property. And similarly, how do you know that your erasure function makes sense, right? Because here, as we said, you could have swapped the two branches, for instance, and then it's still type checked because you're throwing away information anyways, but morally you've changed the meaning of the program. So one thing you could do, and this is going back to the evaluation function being assigning a meaning to a term, to a piece of syntax, by producing a value in a domain, is to say, well, this erasure function better be compatible with evaluation. So if you think about it, if I evaluate my typed function before erasing it, this will give me a value. And if I evaluate the expression after having erased the types, I should get the same value still, because the computational behavior of the program described doesn't depend on all of the invariants that are enforced. It only depends on the constructors you've actually used. So you could prove something like this. So erase correct, saying that full expression of type T, if I t-val, well, okay, no, I need to get this the right way around. If I eval the erasure of E, then I should get just, and this is where it's annoying, t-val E. Okay, I guess I can put a hole and then we can look at it. So if I try to put just the value computed by t-val here, let's see, it's this. Whoop. So the problem is that I want eval, which is the result of running eval, but what I have is a typed value. Luckily, we should be able to write a function that does that. So tval t2val, and it will look silly because it's not actually doing any interesting computation, right? It's just wrapping things around in the appropriate injection. So, oh, okay. So if my typed value is a Boolean, then the corresponding value is bool of that value. And if my typed value is a natural number, then the corresponding value is nat of that value. And here I should be able to say embeds of this thing. So it's always a good exercise to, when you're defining these new notions, try to think of how could I express the fact that it is the right one? Because the types here are loose enough that you could implement an awful lot of things, right? You could have a constant function, etc. But then you would be breaking the moral invariant you have with the idea that this is an erasure function. It's only throwing away useless information. Well, useless. It's only throwing away extra information, but keeping the essence of the program. So yeah, if you want to have fun, you can try to prove these things. That might be interesting. And then, so okay, why do we go through computing a well-typed representation if evaluating the typed value is just exactly the same as evaluating the original one? Well, because now we can actually perform transformations on that piece of syntax, and we only need to consider the cases that make sense, because all of the garbage programs will have been thrown away during type checking. And so it's not only about evaluating, it might be about transforming the syntax in a compiling process, for instance, and eventually you want to emit code in a different language. And in all of these intermediate steps, you don't want to have to deal with all of the nonsense that might have come in from the user input. You want to work with really strong invariants. And okay, so here we have this reduce f function. So this is an example of an optimization path. Of course, here it's a bit silly because all of our expressions, if you think about it, they are closed. They're only using if, add, etc. on literals eventually, or they're using it on expressions which themselves are using literals. So everything could just compute away to a single constant. But the same principles still apply in more complex settings. So I'm going to start from an arbitrary expression. Oh. Okay. And then I want to reduce the if then else. All of the if then else with a concrete value inside, I want to crush them. So I can look, I don't know, this one is not going to move, this one is not going to move.
Should we save this for next week? Maybe?
Should we? Okay. I was hoping
it's a
to.
shame rush through it.
Yeah, okay. Well, think, so third challenge, right? You have erasure is correct, you have typing is unique, and then if you want to go have a go at optimizations, you can